Hello, this is Ryunha, and today I will introduce you the paper React Synergizing Reasoning and Acting in Language Models accepted in ICRL 2023. Recent studies show that LLM reasoning has evolved in two main directions. The first focuses on reasoning-only structures like chain-of-thought prompting. Properly prompted large language models can perform multiple reasoning steps to solve arithmetic, common sense, and symbolic reasoning tasks. Here, the model relies solely on its internal representations without grounding in the external world. This limits reactive reasoning and knowledge updating and can cause issues such as factual hallucinations and error propagation. The second direction uses pre-trained language models for planning and acting in interactive environments. Typically, a language model generates domain-specific actions or plans, which a controller then selects or executes. However, these approaches do not use the model to reason abstractly about high-level goals or maintain a working memory to guide actions. So far, no study has explored how reasoning and acting can be combined synergistically for general task solving, or whether this combination provides systematic advantage over reasoning or action alone. To address this, the authors propose REACT, a general paradigm for combining reasoning and acting with language models to solve diverse language reasoning and decision-making tasks. REACT prompts LLM to generate both verbal reasoning traces and task-specific actions in an interleaved manner. This enables the model to perform dynamic reasoning, creating, maintaining, and adjusting high-level plans for actions, which refers to reason to act, while simultaneously interacting with external environments such as Wikipedia to incorporate additional information into its reasoning, referred as action to reason. The main contributions of this work can be summarized as follows. First, the authors introduce REACT, a novel prompt-based paradigm that combines reasoning and acting in language models, enabling them to solve general tasks more effectively. Second, the paper presents extensive experiments across diverse benchmarks. This shows that REACT outperforms prior approaches that focus on either reasoning or action generation alone, particularly in a few-shot learning setup. Finally, the authors perform systematic evaluation and analysis to understand the importance of acting in reasoning tasks and reasoning in interactive tasks. Before explaining the REACT method, it is important to first describe the architecture of a general task-solving agent. At time step T, an agent receives an observation OT from the environment and selects an action AT according to some policy pi, where CT stores all previous observation and actions. This context serves as the agent's memory. Learning a policy is challenging when the mapping CT to AT is highly implicit and computationally intensive, which can cause the agent to generate incorrect final action or continue producing hallucinated actions. REACT addresses this by augmenting the agent's action space with a large language space L. An action AT head in this language space, referred to as a thought or reasoning trace, does not affect the external environment and therefore produces no observation feedback. Instead, a thought AT-head is used to compose useful information by reasoning over the current context CT, updating the context to CT plus 1, which is CT and which includes CT and AT-head to support future reasoning and actions. However, since the language space L is essentially unlimited, learning in this augmented action space is challenging and requires strong language priors. To address this, the authors employ a frozen large language model prompted with few shots in context examples to generate both domain-specific actions and free-form language thoughts for task solving. Each in-context example consists of a human trajectory of actions, thought, and environmental observations used to solve a task instance. For the example of thoughts at AT-head, as shown in this figure, there could be various types of useful thoughts, such as decomposing task goals and create action plans, injecting common sense knowledge relevant to task solving, extracting important parts from observations, track progress and transit action plans, handle exceptions and adjust action plans, and so on. Since decision-making and reasoning capabilities are integrated into a large language model, React offers several unique advantages. First, it is intuitive and easy to design. Designing React prompts is straightforward because human annotators simply type their thought in natural language. Second, it is general and flexible. React can handle a wide range of tasks, even though with very different action spaces and reasoning requirements. Third, it is performant and robust. React shows strong generalization to new task instance while learning solely from 1 to 6 in-context examples, consistently outperforming baselines with only reasoning and acting across different domains. Finally, React is human-aligned and controllable. React promises an interpretable sequential decision-making and reasoning process where humans can easily inspect reasoning and factor correctness. Moreover, humans can also control or correct the agent behavior on the go by thought editing. Here, I will compare React's performance on knowledge-intensive reasoning tasks such as multi-op questions answering and fact verification against other baselines. By interacting with a Wikipedia API, React can retrieve information to support its reasoning while simultaneously using reasoning to decide what to retrieve next. This demonstrates a clear synergy between reasoning and acting. The authors evaluate React on two datasets, Hotpot QA, a multi-hop question answering benchmark that requires reasoning over 2 or more Wikipedia passages. Favor, a fact verification benchmark in which each claim is labeled as supports, refute, takes, or not enough infos, depending on whether a Wikipedia passage exists to verify the claim. This study adopts a question-only setup for both tasks. Models receive only the question or claim as input without access to supporting paragraphs and must rely on their internal knowledge or actively retrieve information from an external environment to support reasoning. For Hotpot QA and Favor, the authors randomly selected 6 and 3 examples from the training set, respectively, and manually created React format trajectories and few short examples. Each trajectory contains multiple thought, action, observation steps. They then modify these trajectories to create several baselines. In standard prompting, refers to as standard, all thought, actions, and observation are removed. In chain of thought prompting, referred to as COT, actions and observations are removed, serving as a reasoning only baseline. In COT with self consistency, referred to as COTSC, multiple reasoning paths are generated and the majority vote is used to select the most consistent answer, improving overall performance. In acting only prompting, referred to as ACT, thoughts are removed. This method operates in a different task and action space using imitation and reinforcement learning instead of prompting. React produces more factually grounded answers, while COT demonstrates strong reasoning abilities. To leverage both, the authors integrated React and COTSC. The model can switch between them as needed. If React fails to find the correct answer within a set number of steps, it switches to COTST. If the model lacks sufficient internal knowledge to confidently solve the task, it returns to React. Looking at the results, React outperformed the ACT baseline, which relies solely on actions on both knowledge-intensive reasoning tasks, hotpot QA and Fever. This demonstrates the significant value of reasoning in guiding actions and synthesizing final answers. Even in fine-tuning settings, reasoning traces provide more informative guidance to actions, contributing to improved performance. Moreover, the combination of React and COTSC achieved the best results on both hotpot QA and Fever. Switching from COTSC to React performed best on Fever, and switching from React to COTSC performed best on hotpot QA. These results highlight the importance of effectively combining the model's internal knowledge with external knowledge acquired through reactions tasks. Next, the authors analyzed the types of successes and failures on React and COT. COT suffers from several hallucination issues, resulting in much higher false positive rate compared to React. In fact, 56% of COT's major failures were due to hallucinations. React, on the other hand, can access external knowledge sources such as the Wikipedia API, making its problem-solving process more factually grounded and reliable than COT. However, due to the structural constraints of interleaving reasoning, actions, and observations, React sometimes exhibits higher reasoning error rates than COT. This is particularly evident when the model gets caught in loops, repeating previous thoughts and actions. Furthermore, for React, successful retrieval of useful information is critical. Inefficient searches can disrupt the model's reasoning and accounted for 23% of errors in the study. The second set of tasks used to evaluate React are two language-based interactive decision-making tasks, ALF World and Webshop. Both involves complex environments that require agents to act over long horizons with sparse rewards. ALF World is a text-based game set in a simulated virtual household environment. The tasks in this environment are complex, involving more than 50 locations and requiring over 50 actions. Agents must engage in long-term planning, track sub-goals, and perform semantic exploration. In particular, leveraging the LLM's common sense knowledge is crucial for reasoning about where typical household objects might be located. Webshop is an online shopping website environment containing 1.18 million real-world products and 12,000 human-written instructions. The environment features a wide variety of structured and unstructured texts, and agents are required to purchase a product based on a user instruction by interacting with the website. The experimental results show that React outperformed Act on both benchmarks. In IELF world, even the lowest score of React, 48%, was higher than the performance of Bertler, which uses Act combined with imitation learning. In Webshop, using only Act already achieved better results than IRL or reinforcement learning, but React further improved performance by approximately 10%. React was able to bridge the gap between noisy observation and actions through reasoning, allowing it to identify products and options that matched user instructions more accurately. However, it still fell short of human expert performance, as humans can perform much more extensive product exploration and query reformulation. React represents the first attempt to combine reasoning and action in large language models. Unlike previous inner monologue approaches, which focus solely on environmental observation and goal verification, React enables more flexible and diverse reasoning. Evaluation studies confirm that React significantly outperform IAM-style external feedback methods, particularly in evaluating sub-goal completion and inferring object locations using common sense reasoning. This advantage helps explain why React achieves superior performance across tasks. In summary, this paper proposed React, a simple yet powerful method that integrates reasoning and acting in large language models. Through experiments on multi-hop question answering, fact-checking, and interactive decision-making tasks, they demonstrate that React achieves superior performance while also providing interpretable decision trees. Despite its simplicity, handling complex tasks with large action spaces requires many demonstrations, which often exceeds the input length limit of in-context learning. Looking ahead, scaling up React with multitask training and combining it with reinforcement learning or other complementary paradigms could lead to much stronger agents, unlocking the broader potential of large language models for diverse applications. So, thank you for listening today.